Let's look at OpenStax University Physics Volume 2, Chapter 10, Problem 37. Consider the circuits shown below. A. What is the current through each resistor in part A? B. What is the current through each resistor in part B? And C. What is the power dissipated or consumed by each circuit? D. What is the power supplied to each circuit? So we have these two circuits, and it looks like they have the same resistors, they have the same power supplies, except V2 is backwards for these two circuits. So we will have to solve these problems separately, and I'm going to start with part A first. So the first thing I will do is choose directions for currents through the different resistors. I will say that I like to keep, since I have a resistor R1, R2, and R3, I like to call the current through resistor R1 I1, current through resistor R2 I2, and current through resistor R3 I3. So that's the only thing that I'm taking into consideration here when I pick the currents. So I need current I1. Let's say that this is I1 going through R1. Let's say that the current I2 goes this way, and current I3 goes that way. So then I can automatically write Kirchhoff's junction rule, which says that sum of the currents into the junction equals sum of the currents out of the junction. So the currents going into the junction are I2, and that's it. So only I2 goes into the junction. I1 and I3 come out of the junction. So into is I2, out of are I1 plus I3. Now, based on these currents, I can write down the pluses and minuses on the resistors, the higher potential and the lower potential end of the resistor. So I know that this end of the resistor will be positive and this end will be negative because the current goes from high potential to low potential. That means that this end of the resistor is positive and that is negative, so it's at the lower end is at the higher potential, and this end is at the higher potential, that end is at the lower potential. So now I have labeled my resistors, and I'm going to now pick two loops. So I'll go clockwise through this left loop, and I'll use Kirchhoff's loop rule, which says that sum of the potential drops equals sum of the potential rises. Drop is when we go from a high potential to a low potential. Rise is when we go from a low potential to a high potential. So going through the left loop, let's say that I'm starting at the corner here. The first thing I'm encountering is the V1, and I'm going from negative to positive. That is a rise. Then I'll go through resistor R1 from negative to positive, and that is a rise. And then I'll go through R2 from negative to positive, and that is a rise. So it looks like I did something wrong, and I don't care, because I have a 0 for the potential drops, and all the other potentials are rises. So I have V1 plus I1 R1 plus I2 R2. Now, why don't I care? Well, the mistake that I made is in choosing one of these currents or two of these currents. And there's no way I can know the correct direction for the currents. So I see that something is wrong here, but it doesn't really matter, because when I solve for these currents, I will get a negative number at some point and know that that was my wrong current. So I'm just going to leave it like this and keep on going with the next loop. So I'll go through the next loop in clockwise direction again, and I'll start up here. So it looks like I have a potential drop, a potential rise, and another potential drop here. I'm going plus, minus, minus, plus, plus, minus. So let's see. The first thing that I'm encountering is V2, and that's a drop. So I have a V2 on this side, and then I have a rise, which is I3, R3, and then I have a drop, and that's I1, R1. So here I have my three equations and three unknowns. So I have the currents, and I have two potential drops. So now I have to go about solving this. So how do I solve things? Well, from the currents, I can substitute wherever I see an I2 with I1 plus I3. So that happens right here. So I will have 0 equals V1 plus I1 R1 plus, instead of I2, I will have I1 plus I3. So it's I1 R2 plus I3 R2. And then I still have the second equation, V2 plus I1 R1 equals I3 R3. I like to keep my equations together so that I know what I'm working with. So now from the second equation, I can solve for I3. So I3 is V2 plus I1 R1 divided by R3. And now I have an expression for I3. I can plug it into here. And then I have 0 equals V1 plus I1 R1 plus I1 R2 plus I3. So that is V2 plus I1 R1 divided by R3 times R2. So let's multiply both sides by R3. So we have 0 equals V1 R3 plus I1. I'm going to factor out R1 plus R2 times the R3 that we multiply both sides by, plus V2 R2 plus I1 R1 R2. So I can now solve for I1, and I1 will be negative V1 R3 minus V2 R2 divided by R1 plus R2 times R3 plus R1 R2. So that is negative, okay, what's V1? 1.6. R3 is 1,000. V2 is 1.4. And R2 is 1,000. Divided by R1 plus R2. So that's 1 plus 2. That's 3,000 times R3, which is 1,000, plus R1, that's 2,000, times R2, that's 1,000. So when I do the calculation, I end up with I1 being negative 0.6 milliamps. So I found my problem, maybe one of my problems. I see here that the current that I have for I1 is negative. That means that my I1 should have gone in the opposite direction. So I would say as an answer to the problem that I1 is 0.06 milliamps down through resistor R1. But for now I'm going to leave it like this because I have to use this same value to solve for the other currents. So I3 over here is V2, that's 1.4 volts, plus I1, this negative 0.6 milliamps, times R1, which is 2,000, divided by R3, which is 1,000. So we end up with 0.2 milliamps, and thankfully I picked the direction of this current correctly. So I3 is going indeed to the right at that junction. So now I have I1 and I2, I'm sorry, I have I1 and I3, so I can find I2. So that is negative 0.6 plus 0.2. So that's negative 0.4 milliamps. And guess what? I've picked the direction of that current wrong as well. So the correct direction for the currents would have been I1 down, I2 to the left, and I3 to the right. So those were my mistakes, but they're not really mistakes. There was no way for me to know whether those currents were correct or not. All right, so we are done with part A. We know the currents through the circuit on the left. Now we have to do the same thing for the circuit on the right. So again, I'll start out by picking currents, and I'm stubborn, so I'm going to still go with I1 going up. I'll go with I2 going in this direction and I3 going in this direction. So I picked the exact same direction of the currents. I'm going to have to now label the resistors, and since I picked the same direction for the currents, my resistors are going to be plus minus like this, plus minus there, and plus minus here. I'm just copying them from the other diagram that we have. So I can write Kirchhoff's junction rule again, and it's the same that we had before. I2 equals I1 plus I3. And now I will pick loops, and I'll do this one again like this. And since nothing is changed in this is different in this loop, I have the same thing as in the previous part. So 0 equals V1 plus I1 R1 plus I2 R2, which is still wrong. I haven't learned apparently. No, I did it on purpose. All right, and then the loop on the right will be a little bit different. So if I go this way, starting at that point, what is changed is the V2. Here it was a drop, there it's a rise. So I'm going to have to put that on the rise side. So we have I1 R1 as the only drop, and then on the rise side I have V2 plus I3 R3. So here are my three equations, and I'm going to solve them the same way that I did before. I will substitute I2 into the other two equations. So then I have 0 equals V1 plus I1 R1 plus I2, which is I1 R2 plus I3 R2. And then from the second equation, how about this time I solve for I1? So I1 is going to be V2 plus I3 R3 divided by R1. And I'll substitute the I1 into the green equation. So then I have 0 equals V1 plus. Now I1 is V2 plus I3 R3 divided by R1. And if I factor out I1 here, then I have to multiply this I1 by R1 plus R2. So R1 plus R2 plus I3 R2. Now let's multiply both sides by R1. So we have 0 equals V1 R1 plus V2 R1 plus R2 plus I3 times R1 plus R2 times R3 plus I3 R1 R2. Okay, so solving for I3, it's negative V1 R1 minus V2 R1 plus R2 divided by R1 plus R2 times R3 plus R1, R2. So V1 is 1.6, so this is negative 1.6 times R1, which is 2000, minus V2, 1.4, times R1 plus R2, that is 3000, divided by R1 plus R2, I just said was 3000, times R3, which is 1000, plus R1, that's 2000, times 1000. And I have to really squeeze things in here. So now, so we get 1.48 amps, and those are negative. All right, so now we have I3. We can find I1. So I1 is, what's V2? 1.4 plus I3, negative 1.48 milliamps, times R3, and that is 1 kilo ohm, divided by R1, which is 2000. And we get negative 0.04 milliamps. So this one is also negative. All right, so then what do we get for I2? I2 is going to be also negative, so all my currents are in the wrong direction for this circuit, and that would be negative 1.52 milliamps. Okay, so now we have the currents, and I know that they should have gone all in opposite directions. So my I1 should have been down, my I3 should have been to the left, my I2 should have been to the left, like that. But we found the currents, and we know the directions now too. All right, now in part C, we want to know the power dissipated by each circuit. So power dissipated is going to be the energy that's used by the resistors. So we have to figure out the sum of I squared R for all three of these resistors. So let's do that. So for circuit A, I should make some space here. For circuit A, I have I1 squared R1 plus I2 squared R2 plus I3 squared R3. So I1 squared is 0.6 times 10 to the negative 3 squared times R1, and that is 2000, plus I2, that is negative, but we're squaring it so it doesn't matter, 0.4 times 10 to the negative third squared times resistor 2, that's 1000, plus I3, which is 0.2 milliamps, so 0.2 times 10 to the negative 3 amps squared times 1000. And when we do the math, then we get 0.92 milliwatts. Now, if we do the same thing for part B, so this is really C part B, we have, again, I1 squared R1 plus I2 squared R2 plus I3 squared R3. So I1 squared is 0.04 milliamps squared times R1, that's 2000, plus I2 squared. I2 is 1.52 milliamps squared times 1000 plus I3, and that's 1.48 milliamps squared times 1000. So when we plug in the numbers into our calculators, we get 4.5 milliwatts. Now in part D, we want to know how much power was supplied to each circuit. So that would be the voltage times the current produced by this power supply plus voltage times current produced by this power supply. That's for the first circuit. And we do the same thing for the second circuit. And we notice that had we only had one power supply here in the circuit, it would have produced a current going this way. And that's what we have here. If this were the only power supply, it would have produced a current going in this direction, and that's the direction of the current we have here. Now, in the other circuit, the power supply produced a current, would have produced a current going in this direction, and that's what we have. And here we would have had a current going in this direction, and that's what we ended up having here as well. So let's do the calculations now. So for circuit A, we have V1 I2 plus V2 I3. So that is 1.6 volts times 0.4 milliamps plus 1.4 volts times 0.2 milliamps. And this will give us 0.92 milliwatts, which is kind of what we were expecting. And that's because the power supplies in this circuit were supplying 0.92 milliwatts of power, and the resistors in the circuit used up 0.92 milliwatts of power. So it's a good thing that these two values agree with one another. For part B, we have again V1 I2 plus V2 I3, and that is 1.6, and this time I2 is 1.52 milliamps, and V2 is 1.4, and I3 is 1.48 milliamps. So we're getting 4.5 milliwatts, and again, that is a good thing, because that means that the amount of power supplied by the power supplies is the amount of power that was consumed by the resistors in that circuit.